Hi, everyone. So welcome to the seminar on intersecting audio AI trust, security, and privacy. I see a few people are still joining, but I'll go ahead and get started. My name is Jennifer Williams, and I'm an assistant professor in the School of Electronics and Computer Science at the University of Southampton. So I want to begin by playing a video for you of the very first speech synthesis system from, believe it or not, 1939, and this is the Voter, created by Bell Labs and initially showcased in the World's Fair in 1939. So here is the first speech synthesis system.
The machine uses only two sounds produced electrically. One of these represents the breath, the other the vibration of the vocal cords. There are no phonograph records or anything of that sort, only electrical circuits such as are used in telephone practice. Let's see how you put expression into a sentence. Say, she saw me, with no expression.
She saw me.
Now say it in answer to these questions. Who saw you?
She saw me.
Whom did she see?
She saw me.
Did she see you or hear you?
She saw
Okay, so
me.
that is an example of the very first speech synthesis system, and that was followed up by the IBM shoebox for speech recognition. So we're talking about speech generation and speech recognition, and boy, have we come a long way since these first technologies. Nowadays, we have a wide variety of different audio AI technologies. So everything that we're familiar with from, for example, Zoom, which is recording this session now, FaceTime and YouTube, TikTok, earbuds that can be used as an entertainment device or as a hearing assistive device, virtual reality, devices in the home, smart watches, and things like that. So we know that the speech technology landscape is very rich, and it's becoming increasingly difficult to opt out of using speech technology. So the solution that I'm talking about in this webinar is that we need more privacy capabilities in order to protect people and foster a sense of trust in these technologies. So this is a bit of a self-introduction about me. Since January 2020, I've been a senior speech scientist at a startup called My Voice AI based in London. And since March 2022, I've been working at the University of Southampton and recently became an assistant professor. My research activities, which I'll talk about in this presentation, include a project on trustworthy audio, which is a one-year project funded by the UKRI TAS Hub. That's a Trustworthy Autonomous Systems Hub. I also work on human perception of voice anonymization and a newer project called Tame Pain, which I'll present near the end. And that is a 15-month project, which is a US-UK collaboration with researchers based at the University of Texas, Austin. Some of my activities within the International Speech Communication Association include I'm the chair of the Special Interest Group on Security and Privacy in Speech Communication. I'm also a co-organizer for the Postdoc and Early Career Research Advisories Committee and a co-organizer for the Young Female Researchers in Speech Workshop. And this year, I'm the senior area chair for the InterSpeech 2023 special sessions. I also have 2 patents. They're published, but still pending. And those are on the topic of voice-based speaker verification on edge devices, and one more patent in the works. So this is an outline of my talk today. I'll give an introduction. I'll talk about trust in audio AI systems. Then I'll talk about safety, security, and privacy. And finally, smart environments. And then we'll summarize with some outlooks and ways to engage. So to begin, speech and audio processing really did originate from electrical engineering, but nowadays we're seeing radical shifts towards interdisciplinary work. Some of these are very recent. So for example, in the field of medicine, we have things like COVID-19 detection and diagnosis, depression detection, analysis and treatment of PTSD, ALS, psychosis, and of course, speech therapy. We also have a lot of different assistive devices like screen readers for the blind and generating captions automatically and enhancing speech for the deaf and hard of hearing communities. And things we're very familiar with are like Q&A devices and GPS navigation. In terms of security, there's a lot of different research efforts going on. So we have verifying the authenticity of audio recordings, for example, in court cases or legal cases. The use of voice biometrics, which can replace passwords, so it'd be a spoken password, voice over IP, and things like that. In terms of autonomous machines, which I'll talk a little bit about, we have scene analysis, so audio scene analysis. Deepfakes is a really big topic lately, especially. So deepfakes are viewed by some as a form of artistic expression, but also a form of parody and humor. And what we see a lot in the news is the use of it for fake media. In the legal and ethics domain, there's a lot of interesting questions around speech technology and speech data. So what happens to our voice data after death? And how do we treat voice as a form of intellectual property? Is that even an issue? And I'll talk about more of that. So I want to encourage people to see the interdisciplinary work as not necessarily a broadening of techniques and research, but more of a narrowing. And that's why I'm showing on the right this Venn diagram of when we work in an interdisciplinary way, we're actually narrowing the focus and scope of research. So speaking of working across disciplines, there's this famous saying, to go fast, go alone, but to go far, go together. And I'd like to say, let's go far. So other disciplines understand issues differently compared to those working in computer science and AI. But sometimes those understandings are limited to discovering vulnerabilities of products after they're developed. When we work across disciplines, it helps us identify important gaps that technicians and computer scientists or speech scientists don't always recognize in the research and the products. And this brings fresh new ideas and perspectives that speech researchers can then implement. And ultimately, we get bigger impacts with the research dealing more with the why question. And here's 3 examples of strongly interdisciplinary research. So some companies are interested in sonic branding. So this is a marketing, really a marketing issue. When you have sonic branding, there's sounds that we learn to associate with a particular company. The second one, what are the legal protections for speech-based intellectual property? And I'll have an example in a bit about a type of voice that was reconstructed, and who owns that intellectual property? Is it the algorithm or is it the voice itself? And third, what should happen to voice data after a person is deceased? These are some big issues, and they go really beyond the scope of computer science. So next, I'll talk about trust in audio AI systems. I like to show this slide, especially to students, because one of the challenges that we're working with right now is that real-world applications require very efficient solutions. And what I mean by that is that a lot of the speech technology that we develop on large compute clusters ultimately will be marketed and turned into products on edge devices. These edge devices have limited power, limited memory, and they require very low latency. But most of the prototyping that we do as researchers is resource intensive. So when we do our research and development, we need to keep in mind the whole product life cycle of how does our idea go from just an idea and some experiments, and how will it be used later? So I like to encourage people to think about sort of a feedback pathway that would help us look at more deeply the what, why, and how. So as researchers, we often live on the left side of this diagram in the prototyping world, where we have an idea, we run some experiments, we have a technique and it works and it gives us some good experimental results. And that's usually where we stay as researchers, especially PhD students and sometimes even postdocs. But what's really important is that some of those ideas can be commercialized. And when they're commercialized, we end up with users. And it's important to ask ourselves early on in the prototyping stage, is my technique fair? Is it inclusive? Does it have some vulnerabilities for users? And does it meet the user needs in a safe manner? So I like to look at this as a feedback pathway and say that we can have these considerations about the user and also about commercialization early on in the prototyping stage. And that's what a lot of my research is about. And on the left, I have some examples of edge devices. So earbuds and hearing aids are one of the best examples of edge devices for speech technology. And we're living in a world now where we have chips that are so small, for example, smaller than a US penny. And we're working in the realm of kilobytes, not necessarily megabytes or gigabytes, which is what we're used to when we're in the prototyping stage. So I want to introduce one of my projects on the UK Trustworthy Autonomous Systems Hub. And this project is the co-design of context-aware trustworthy audio capture. On the right is my team. And what we're doing is we're developing an interactive audio survey that will probe people's viewpoints of trust in a variety of different contexts and scenarios where audio capture takes place in the real world, or that it could take place in some imagined scenarios. From there, we're going to cross-link the perceptions of trust from 3 different areas: the general public, technology developers who work in industry, as well as artists who use audio and sound as a creative medium. We will then take that analysis and develop recommendations for AI regulators and policymakers that really capture trust and that might reveal existing governance gaps. So we want to see how can we increase individual rights and voice-related rights based on these scenarios and the technologies that we talk about in the survey. So we have an industry advisory board consisting of a variety of companies, so Spotify, Bose, Amazon, and Paper Cup. We also have an artist in residence at the University of Nottingham. Now, the team is strongly interdisciplinary, which is really exciting because as a computer scientist, I get to work with other disciplines. So we have several legal scholars. We also have a human-computer interaction and responsible research innovation advisor. And we have a legal advisor who has now moved on from University of Edinburgh to University of Oxford. And we have Gopal Ramcharan as the mentor on this project. So I want to give you some examples of the contexts and scenarios that we're looking at in this survey. And these are 3 examples here: to the public, to industry, and to artists. So for the public, we ask them questions like, do you know about voice transformation in real time? And we give them this scenario. Someone sends a deepfake voice recording to colleagues in the same organization. In these recordings, one of your colleagues seems to speak ill of you. How can you be sure it is real or fake? And then to industry, we ask questions like, is it okay if someone asks you to reconstruct the voice of God? So imagine you work for a company and your boss comes and asks you to create an application that God's voice now has simulated conversations with its disparate people. So can you conscientiously object to that? Do you follow the instructions as you're told to do to keep your job? How do you handle that situation? And then to artists, we ask questions like, how would you feel if a voice was used after death without your consent? Do you believe that audio is blurring the line between fiction and reality? And we give them a scenario. For example, you're a famous movie star. You're asked to give your consent for your performance in future related movie sequels, which would occur after your death. So how do you consent to it? Can you consent to that in a legal sense? And would you consent to that? And I have an example of voice reconstruction, which I'll show in a bit, that really does spark some interesting questions on the ethics, the legality, how can this be regulated? So from our preliminary survey findings, we can draw some early conclusions. We're still running the survey. So most of the respondents that we've surveyed so far, we have 300 responses. Most people believe that their permission is required before their voice is recorded or used. And this is across many of the different scenarios that we presented. But respondents also believe that they have a right to know if their voice is captured, even if it's part of an assistive device, for example, scene analysis for the blind or speech enhancement for the deaf and hard of hearing. So in scene analysis, you'd have an AV system that would translate the visual information into audio. And for the speech enhancement, you'd have different types of technologies that would, for example, enhance a specific voice perhaps from a distance as well, so that someone who was not able to hear could hear better. Now, people who use assistive devices also have the right to use that technology regardless of people's individual privacy concerns. So this is our first contradiction in our survey. So people have kind of differing views. They think, they need to know when their voice is captured and under what circumstances. But then they also believe that others have the right to use assistive technology. We see that strong correlation start to diminish when we look outside of assistive devices, and I'll have more information on the analysis once we've completed this project. So now I want to play a video of, this is Val Kilmer's reconstructed voice. I'm not sure how many people are aware that Val Kilmer, one of the movie stars in the movie Top Gun, fell ill, and in order to have his performance in the movie, a company called Semantic, which is one of my industry partners through Spotify, has used speech technology to take old recordings of his voice and give him a new voice so that he can say new words. And I'll play the video. It explains a little bit more.
We all have the capacity to be creative. We're all driven to share our deepest dreams and ideas with the world. When we think of the most talented creative people, they speak to us in a unique way. A phrase we often hear is having a creative voice. But I was struck by throat cancer. After getting treated, my voice as I knew it was taken away from me. People around me struggle to understand me when I'm talking. But despite all that, I still feel I'm the exact same person, still the same creative soul. The soul that dreams ideas and stories constantly. But now I can express myself again. I can bring these dreams to you and show you this part of myself once more. A part that was never truly gone, just hiding away.
Okay. So that's a very sweet story, and it's quite a feat of technology that this company was able to reconstruct his voice from old recordings. It's really incredible, and that it sounds quite human-like is also quite incredible, and a very good use of such technology. But on the flip side, we can imagine with techniques like this out there where voices can be reconstructed and words can be put into people's mouths, so to speak, in the world of deepfakes, what implications this may have for other realms like fake news and misinformation. And then how does this type of intellectual property function? How should it function? We don't know, of course, the details of what Val Kilmer may have signed when he had this voice reconstructed, but it does raise questions about, can his voice now be used after his death? Because they can, in fact, recreate his voice. It sounds quite like him, to be honest. So this technology is amazing, but when it comes to trust, privacy, security, and these issues, there's a lot more questions than there are answers. So speaking of which, I'll now talk a bit about safety, security, and privacy. So there are no established definitions of privacy and security. So I've adopted some from the law domain. So we take privacy to be controlling access to information, and security, we'll take that to be how information could be used or misused. Now, this is really important for speech because in the speech signal itself, there's a variety of types of information. So there's things like you can detect a health condition, you can detect depression, you can detect COVID, asthma, other things like that. You also get voice identity. So in applications where voice is used for secure access, for example, with phone banking, where you say, my voice is my password, that's a form of voice identity using voice prints. You can also get information about a person's emotional state, their accent, which can potentially lead to discrimination, the age, gender, and many more other types of information. For security, this is quite interesting because there's been continual improvements in the audio technology, like we just listened to with Val Kilmer's voice. And because of those advances in speech technology, it does invite an opportunity for disruptions of privacy and security, such as deepfakes and impersonation. So I like to present this privacy, security, convenience paradigm because what we want is to have privacy, security, and convenience balanced, for example, as an equilateral triangle. We want to have those as balanced as possible without interfering with the technology's usability and convenience. In terms of safety, security, and privacy, these are elements that feed into trust. So one of the challenges that we have is how do we develop efficient and objective metrics that can be used for compliance and assurance? So how do we assure that something has in fact protected privacy or that it is in fact secure? So we need to identify all the special cases where privacy is difficult to assess with a single measure. And this is one of the open challenges in the field of speech technology right now, because some of it depends on the use case and the technology and the context of that technology being used. Now, safety is a tricky one. I think this is a blanket term. So it can encompass things like fairness, assurance and compliance, personalization, and design. And I like to think about these topics in terms of reliability, customization, and privacy by design. So if we take the first one, reliability, we can do things like data degradation, where we have, for example, a noise that we can add to the speech signal, where it would perform very well in some task, some target task, and perform very poorly in some adversarial task. And this is what a lot of people are doing with privacy right now. Not necessarily adding a noise, but they're degrading the data in such a way that they can adversarially detect if information is present or absent. And the second one, customization, we can use a masking algorithm. So this is something where we remove information, specifically a type of information from the signal, and then go ahead and input that result into some target task. In privacy by design, this can be something like a secure enclave that would prevent information leakage within a device. But all of these open up a question of who is responsible for fostering the trust. Is it the researcher who is in the prototyping stage, like I talked about earlier, who's trying experiments, designing algorithms, and just seeing if they work? Is it the manufacturer who's making products and selling them? Is it the government and regulators and policymakers? Is it the user? So these are again open questions. So I'll talk a little bit about speaker privacy. So speaker privacy seeks to remove speaker-specific information from the speech signal. And we did some experiments with this where we extracted an embedding for several utterances. We calculated a cosine similarity between the embeddings, and then we asked humans to rate how anonymized the voice sounds. Typically, speaker privacy is only evaluated with other adversarial technologies like speaker recognition or speaker verification. So getting humans to rate anonymization is a new type of problem. And I'll go ahead and I'll play an original speech sample here. And this is what we're trying to anonymize, by the way.
Throughout the centuries, people have explained the rainbow in various ways.
Okay, so that's a sentence. What we want to do is make that speaker sound not like that speaker. And we have different baselines here, B1A, B1B, B2A, B2B, and those correspond to baselines in the voice privacy challenge. So we want to get that speaker to sound like someone else, and while still preserving other characteristics like the content and the prosody and things like that. So let's listen to how these baselines have anonymized the voice.
Throughout the centuries, people have explained the rainbow in various ways.
Throughout the centuries, people have explained the rainbow in various ways.
Throughout the centuries, people have explained the rainbow in various ways. Throughout the centuries, people have explained the rainbow in various ways.
So B2A and B2B both sound quite similar. B1A sounded very mechanical. You can tell it's synthetic speech. So this is an experiment that we did where we played these samples in a survey, and we asked humans to rank how similar each of these voices were to the original sample. And what we found is that when we didn't give them any information about what we think the similarity is in terms of cosine similarity, they performed not too great. Then when we gave them a bit of what we call AI assistance, where we provide them with our judgment from cosine similarity of how similar the voices are, they tend to get the most similar, the rank 1 most similar voices identified correctly. But they didn't completely trust our cosine similarity scores. So if they did trust it fully, we would see a perfect correlation with all of the AI assistants corresponding perfectly to the cosine-based rankings, and we didn't find that. So what we think is that people were not trusting the cosine similarity as the best way to rank the similarity of these voices. So we're still doing this research, and it's ongoing. In terms of content privacy, so earlier I talked about speaker privacy, and now I'll talk about content privacy. So the objective of content privacy is to characterize and address the needs according to data transmission and intrusion scenarios. And on the right, I've listed some of those types of scenarios. There's more that did not make this list, but you can imagine, for example, if the transmission type is person to machine, and the intrusion type is a person. An example of this would be an eavesdropper, a person eavesdropping in a public space, listening to someone talk to their smartphone. In a machine to person scenario, you could have a person intrusion, and an example of that would be like a screen reader, where the screen reader is saying information out loud from a website like a bank account or a medical record or something sensitive. And a person is listening to that. So there's a lot of different combinations of how you can have transmission and intrusion. In any of these cases, we're looking at how can we mask sensitive keywords and phrases while that speech is in transmission. And so we're looking at it in terms of a compression scenario where we have a speaker, the speech would be compressed, and during that compression state, we can then get the content and mask it, and then that speech can be resynthesized to mask that information from either a person or a machine. And I'll play some examples of what we've done so far. Now, this is, again, ongoing work.
6 spoons of fresh snow, peas, 5 thick slabs of blue cheese, and maybe a snack for her brother Bob.
So that's the original sentence, and what we'll try to do now is mask certain words, and I'll play different masks for you.
6 spoons of fresh snow, peas, 5 thick cheese, and maybe a snack for her brother Bob.
So the whoosh sound is a speech-shaped noise, and the next one.
6 spoons of fresh snow, peas, 5 thick cheese, and maybe a snack for her brother Bob.
And that is a deletion where we've simply removed the target words. And finally,
6 spoons of fresh snow, peas, 5 thick cheese, and maybe a snack for her brother Bob.
So in that one, the words they sound a little jumbled, and that's because what we've done is we've reversed the signal in the time domain. And we've done that while the speech was compressed with an autoencoder. And what we found so far is that the content masking that we're trying here affects downstream tasks differentially. So while the goal is not necessarily to inhibit automatic speech recognition, we find, of course, that sometimes it does, and it does differently than what we would want. So we're still working on how do we fine tune the content masking technique. And then a bigger question is, how do we evaluate this problem? So I proposed a couple of different ways to calculate the success of a content masking scenario. And yeah, it's definitely ongoing research. So next I'll talk about some smart environments. And I'll start with smart buildings. So what we'd like, a few of us at Southampton, what we'd like is to find a way to enhance smart buildings with what we call audio services. And we want these smart buildings to encapsulate person-centric or citizen-centric technologies. Some examples of the types of things we'd like in a smart building are occupancy and activity detection for heating, ventilation, air conditioning, and energy management. I'll give an example of that in a minute. Also audio scene understanding. So if a person walks in, let's say that they can't see or they can't hear, then we would have some automatic services in the smart building that could provide information about what's going on in the building. We could also get things like real-time speech transcripts and measures of meeting engagement. So how interactive are people during meetings? Sign language recognition, audio-based emergency services, and voice identity access to secure areas. One of the biggest challenges with equipping smart buildings with microphones that can do these types of things is the privacy and security issues, and whether or not people would trust such technologies enough to walk into a building where their speech might be transcribed. So when we look at incorporating audio services into energy management, what we're trying to do is capture occupancy and activity detection within a space. So one of the challenges with buildings right now is that the standard occupancy schedules for offices especially, they're changing. And more emphasis has been put on occupant-centric design and occupant comfort. So what we're looking at Southampton is to understand the trade-offs between occupant comforts and the resource consumption. And we're using a reinforcement learning approach to combine reward functions of the energy and comfort information with the occupancy information. We're looking at this in terms of zones, floors, offices, as well as comfort profiles. And ultimately, we're going to optimize the occupant's comfort with the resources that are consumed to operate the building. And the types of different issues that we're looking at are things like thermal, so the temperature of the room. What do people prefer? Do people have different preferences? The humidity levels, the noise pollution. So if you walk into a building and you have an open office type plan where you can choose your own desk, it may be nice to know that there's an especially quiet area that day. You might want to sit there rather than a different place. So there's a lot of different variables here, and we're looking at what is the best way to aggregate the comfort profiles. Now, for the occupancy information, one of the ways that we're getting that information is through audio. But in order to do that, we need to build trust from people as to whether or not they would ever accept a smart building that's equipped with microphones. And so what we're doing right now is looking at a special case of the cocktail party problem. So in the cocktail party problem, some people may be familiar with this, usually involves a crowded room with a lot of people speaking. And typically the task is to see if you can separate the different speakers or enhance speech in a certain way. In this case, what we're doing is we're trying to count the number of people speaking without identifying the individuals. And the key word here is without identifying the individuals. So we want to do this in a way that preserves people's identity as well as the content of what they're talking about. So the kind of data we're looking at I'll play, this is a spectrogram of 2 people speaking simultaneously.
He moistened the adhesive side.
Okay, and here's what it sounds like when 10 people are speaking simultaneously.
These figures are very
So in order to do this counting, we could of course train a neural network or other algorithm that simply counts the number of speakers, and that's fairly straightforward. There's a lot of different ways to do that. But the key here is to be able to perform that task while also negating the speaker identity and the content. So we've added some privacy mechanisms of shredding and reversal, and this is what it sounds like. Okay, and the next one. Okay, so different combinations of shredding the waveform and reversing it randomly in different places. And this was presented at IEEE ICASP this year. We did this with 5 different types of models. So we had one that was just the raw waveform. We also used the magnitude spectrogram, mel frequency spectrogram, MFCCs, and LFCCs. We trained CNN. The parameters are on the right. We had a different number of convolutional layers. The target that we're trying to predict was a 1-hot vector representing the occupancy, and we had occupancy ranging from 1 to 10 simultaneous speakers. So we're trying to predict how many speakers are in the audio. We found that the raw waveform performed best across all of the different privacy-preserving features. So we're able to predict the number of people in the audio by approximately 1 to 2 people, which is good. But the shredding and shredding plus reversal is important because, again, we're trying to perform this prediction task of counting the number of people while also not being able to identify them individually or capture their content. But this type of problem doesn't have a standard way to measure that type of privacy. So what we did is perform 2 adversarial tasks, speaker identification and automatic speech recognition. So in the speaker identification, we had the original, the shredded, and the shredding plus reversal waveform. And we have a different number of speakers here. So what we found is we would like the equal error rate on the left to be as high as possible. And the values that we were seeing were 10.6, 11.9. While that is in fact not great equal error rate, we would like that to be much, much higher. So that shows us that it's still possible to sometimes identify the speaker, even though we've messed with the waveform quite a bit with the shredding and the reversal. With the speech recognition, we measured match error rate for the speaker counts, and we have here the match error rate. So this is similar to the word error rate, except that it fits between a 0 and 1, so it's a bit more interpretable than word error rate. We have very high degradation of the content. So we're not too worried about the content being captured, but we are worried about the speaker identification being captured. So next, I'll talk a little bit about smart cities. We've just recruited a PhD student who is working on augmented reality soundscape experiences on edge devices. And this is an industry collaboration with Bose Corporation in the USA. And so we take a soundscape to be all the different sounds that contribute to a person's oral experience. And unlike this image, they're extremely complex because we have all of the different overlapping signals. And it's difficult to process the soundscapes in real time with the low latency. And right now, there's no ability for a listener to control which sounds in their environment are enhanced and which are removed. We have technologies like noise cancellation and things like that, but we want to give the listener an opportunity to have finer control. For example, turn up the sound of nature and turn down the sound of traffic, or turn up the sound of traffic, right? There's different objectives in this project. One, of course, is to develop a real-time enhancement and augmentation of sound scenes that can run on ultra-low power edge devices. And then there's the element of giving the user control over their acoustic environment. So this is in progress. Next, I'll talk about smart hospitals. So this is another environment that my research extends to. So we have a project going on right now. It's a 15-month project that will end next July, so in 1 year. It's called Tame Pain, Trustworthy Assessment of Pain, Listening Between the Lines. And this is a collaboration between the University of Nottingham, University of Southampton, and the University of Texas, Austin. This is a team that I'm working with. So we have Southampton, Nottingham, and University of Texas. We have 3 different co-PIs, one at each institution, and the 3 academic institutions. As a team, we represent 9 different disciplines. So Dr. Ganesh Vinswaran, he is a medical doctor in the NHS. Dr. Tina Seabrook is a psychologist. We also have Anna Maria Piscopani. She is a legal scholar. And the rest of us are some form of computer scientists. Liz Douthwaite works in responsible research, innovation, and human-computer interaction. So we have quite a team here. And I'll tell you the problem that we're trying to solve. So this was an observation made by our NHS doctor on the team. He performs procedures on patients who are awake, and he found that not all people can adequately verbalize their pain when they're in a clinical setting. So these are patients that he sees have this problem. And some of the issues related to that are things like speech impairments. He works with stroke survivors. Some people may have cognitive difficulties. They might be very young, or they just don't speak the language. So they can't say, for example, ouch, that hurts, I'm in pain, it's an 8 out of 10. They can't give a clear signal as to their pain level. So our project that we're working on is very much a proof of concept solution. By proof of concept, I mean, we're going to try something and we know that it might not work, but we're trying it anyway because we can. And no one else is looking at this problem quite like we are. What we're going to do is look for acoustic biomarkers in the auditory signal that correspond to a person's reported pain level. And then we're going to explore the cross-cultural pain expressions between the US and the UK. Now that includes the participants in our study will come from the US and the UK, as well as the assessment by doctors will come from both the US and the UK. And we will cross-link those subjects who experience pain with the doctors who are assessing the pain. And we'll try to develop some AI that can analyze the pain from audio and present that with doctors to see how they trust this type of extra signal in their operating room. This is an overview of the phases of the project. So our phase 1 will be a pain induction experiment where we will take healthy subjects because of ethical reasons. We'll take healthy subjects recruited from university. We'll put them through a pain induction procedure and have them speak out loud certain sentences that we then record the audio from. And then in the middle here, we have the system development. We will do some analysis to try to identify any acoustic biomarkers of the pain that they've reported. In phase 3, we will present all of this information to a set of doctors in the US and the UK and see if they agree with 1, the pain reported by the subjects, and 2, the algorithm that we develop that detects the pain level. And what does that look like? So do doctors agree with the algorithm? This is the kind of the final stage of the project. So we'll present doctors with a survey. They will have either video or audio of the people experiencing the pain. They'll have information about what our model predicts. So what kind of pain level did we detect, and do we have a confidence score, how sure we are? And then we will have a trust in AI questionnaire alongside this. So we will ask the doctors, how much pain do you think the person is in? And do you agree or disagree with the pain level that our algorithm has detected? Now, the purpose of this study is not to replace any tools that doctors already have. Doctors have access to oxygen sensors, heart rate monitors, blood pressure, and of course the patient themselves. So what we see this as is another tool in their toolbox when they're in the operating room. It's also useful potentially for 111 calls on NHS, where the operator has only the audio information to make assessments and give advice. So I'll start to summarize here. I'd like to encourage everyone to engage with regulators and policymakers. And a question I like to ask is, who has the most influence on policy and regulation? Is this academics or is this industry? Now, this is particularly important for speech technology because the industry in speech technology right now is booming, and these companies are big. They have a lot of money, and they have a lot of influence. So who has the most influence in the UK? There are some open calls for evidence. So this is stepping a little bit outside of speech itself, which is my topic, but there's a call for evidence on generative artificial intelligence in education, and also how will large AI models shape the future and what is the right regulatory approach. So I'm including this because I'd like to say we cannot avoid participating in this technology regulation. I think we should engage now and use our influence as academics, or what might happen is that we may get regulated in ways that could be counterproductive. And to this end, I organized a workshop in May from the Trustworthy Autonomous Systems Hub, where we invited a variety of different stakeholders. So we had 48 attendees from academia, the UK government, as well as UK regulators. And we had, for example, the Office for AI, Ofcom, NCSC, National Highways, Health and Safety Executive, and CMA. And we had 3 different sessions during the day where we had a problematizing session, solutioneering in domain for different sectors, and then a solutioneering globally, looking for global links in AI regulation that we could talk about. So some of the key takeaways were that regulators need cross-collaboration as well as cross-regulation in order to advise and solve some of the really big problems in AI regulation. There's a need for more evidence gathering and case studies, which is one way that academics can participate and offer their expertise. And so communication beyond policy is also very important for public understanding. I have a follow-on workshop planned for early November, and in that workshop, I'll include some industry stakeholders as well. So to summarize, again, if you want to go fast, go alone, but to go far, go together. Let's go far. I want to continue reimagining how we can use audio as an information source to enhance our everyday life, but also treat issues of trust as the highest priority. It's important to engage across disciplines because the best technical solutions often have multiple applications beyond what we think we're developing. Content privacy is a new and hot emerging research area in speech processing. And there are some really interesting future projects within the University of Southampton, for example, in the realm of psychology. So we have people who would like to help their psychosis patients by allowing them to recreate auditory avatars of their hallucinations in order to help with their treatment of psychosis. This would be extremely experimental, but also really exciting for speech processing and audio processing. And in medicine, accessing an app to help monitor breathing conditions like asthma. So do get in touch if you're interested. I'm open to collaborations. My future outlook is that to develop more reliable and robust privacy metrics. So what's currently happening in the Voice Privacy Challenge, I think, is not enough. We need to do a lot more work in this area, and also protect speech data from misuse. And this is more urgent. So deepfakes and surveillance, how can we protect the speech data from all the different ways that it can be spread to protect individuals and their rights, and developing techniques that are explainable to increase trust in the audio AI technologies. Now, this helps the end user. It helps also people like AI regulators and policymakers. gaining a better understanding of how AI regulation will shape audio technologies, and understanding public concerns about safety, security, and privacy. I also think it's important to expand the existing efforts in privacy and security to more realistic conditions, which right now is not happening in the speech technology field, and ultimately increase this interdisciplinary collaboration. So if you're interested in getting involved, you may have heard there's a Responsible AI UK initiative led by the University of Southampton. They have open calls for funding. I'm the chair of the special interest group for ISCA on security and privacy and speech communication. You can attend a webinar or present. Also, PhD students and postdocs are welcome to present a paper at the monthly cafe if you're not wanting to give a webinar. We have a symposium coming up at Interspeech in Dublin in August that you're more than welcome to attend. And I'm also organizing this follow-on regulation workshop in November. It is invite only, but do contact me for details if you're interested. And we will have people from academia, the UK government, UK regulators, as well as industry in attendance. So with that, thank you very much. And I'd like to open the floor to any questions. Okay, if there are no questions, thank you all very much for listening. I can be in touch. Feel free to be in touch if you have a question that comes up later, if you'd like to discuss anything. Thank you all very much. Oh, sorry, I see 2 questions have come in. Okay, so the first question is, why did you not disguise the voice using other techniques? Is this regarding the speaker privacy, right, Trevor? Yeah, pitch shifting. The techniques that I presented here are the baselines that were used in the voice privacy challenge. It's a challenge, so it's a shared task, and there's multiple different systems submitted each year that it runs. There's a lot of other techniques, so these were just the baselines that those systems are measured against. 2 of them were signal-based, and 2 of them were neural network-based. So yeah, pitch shifting is definitely something to look at. I'm sure some of the systems did use that technique. Yeah. I think that was all the questions. Oh, there's one more. Oh, thank you. Thank you so much. Really appreciate you attending.